So we couldn't really talk about the actual absolute level of utility, and that was because, um, as I've sort of belabored it to for the last couple of weeks, um, utility is not. There's no notion of absoluteness in the scale of the utility, right? We could always take a monotone transformation and we get back some equivalent utility function that's representing the same choice behavior, the same preferences, and would always, every utility maximization problem, you could substitute in one utility function for another, and you would get back the same solution. As long as one is a monotone transformation of the other, which means that the absolute level, the numbers of the utility function are meaningless. We could stretch it out or press it together as long as the order stays the same. Production is not like that. As discussed in the beginning of the first video on production, we can actually go out and observe production functions and therefore really discuss the absolute properties of them, how they grow and change as the inputs grow and change. So the scale or size of output is a very tangible thing, which has a very physical interpretation and therefore is a meaningful property to talk about. So everything we did so far, we did in the utility world. Remember that marginal rates of substitution, and so also marginal rates of technical substitution, are independent of the scale properties of the utility function or production function. If we take monotone transformations, we don't disturb that, and we talked about that at length when we were talking about utilities. So everything we did so far had that analog. Here we're going to talk about something that's really specific to production, and that's because we're going to actually talk about the actual aggregate level of production when we change the inputs and outputs. So we can think about something like, a firm opens a new plant, a new factory, and it's exactly like the old factory. I don't know, say Ford. Ford is building cars, and they have a plant in Detroit, and they say, we also would like a plant in Southern California, and they just open an identical plant. They hire the same kind of people. It runs exactly like the old plant. Another thing could be, a farmer gets twice as many tractors and farmhands, right? They double the number of tractors and farmhands. Another thing could be that Apple hires twice as many designers as they had before, or coders or whatever, to write the operating system. And we could ask in each of these kind of scenarios, what happens to the output, right? Does the output change more or less than the change in input, right? If we change all the inputs by a fixed amount, what happens to the output? And remember that this is sort of like the idea of homogeneity. It's related to the idea of homogeneity, and I'll talk about that in a second. So if we have a production function, we call it increasing returns to scale. If when we multiply the inputs by a fixed factor greater than 1, then the corresponding output increases by more than that same output scale factor. Right? So if t is equal to 2, this says the first line says the production when I double capital and double output is greater than twice the original output. So it more than doubles. So this is increasing compared to linear growth. So if I more than double, I double my inputs and I more than double my outputs, then I'm increasing returns to scale. I'm decreasing returns to scale if the opposite is true. I double my inputs and that less than doubles my outputs. Right, so I multiply both my capital and my labor by 2, and the corresponding output is multiplied by less than 2. And this has to hold for any t, right? So it's not just doubling, it's by multiplication by any scale factor larger than 1. And these relationships would be totally switched around if you just picked scale factors less than 1. That's just an algebraic identity. Something is called constant returns to scale if it's both increasing and decreasing returns to scale, which means that when I multiply both my inputs by a common scale factor, my output is multiplied by exactly that same scale factor, right? So if I double my inputs, I double my output. If I triple my inputs, I triple my output. So increasing returns to scale says I'm getting more for my money, right? I double my inputs, but I get more than twice as much output. Decreasing returns to scale says, I'm losing on this doubling up thing. I'm losing on this doubling up thing because I double my inputs, but I less than double my outputs. And constant returns to scale says it's exactly even all the time. So here's an example. Maybe my production function is like I have to hire 4 people to work on a maybe it's the other way around. I have to have 4 units of capital for each laborer. So my production function is the minimum, this Leontief minimum, perfect perfect complements type production function where I have k and 4l. Notice that this is constant returns to scale. Because either the minimum is equal to k, in which case if I multiply both k and 4l by t, then I get back tk is equal to the minimum, so that's t times the minimum, or the minimum is equal to 4l, in which case when I multiply both t and l both k and l by t, I get back that this minimum is equal to t times 4l, which is t times the minimum between 4 and l. Right? So basically, you can just pull out the scale factor from the minimum. So it's a constant returns to scale. How about a different example that's even more concrete? Let's say f of k and l is just k squared times l, and I'll let both of them be 2. So my output is 2 squared times 2, which is 4 times 2, which is 8. And then if I double both my inputs, now I have k is equal to l is equal to 4. And then 4 squared is 16 times 4 is 64, which is greater than twice the original output, right? 64 is greater than 2 times 8. So I doubled my inputs, and I got more than double my outputs, right? I multiplied my outputs by 8, but I multiplied my inputs by 2. So that's increasing returns to scale. What about a slightly more general example? We can come back to this Cobb-Douglas production function that we talked about from a previous lecture. And we can see that if you multiply both k and l by t, then you can pull out a t in front of the first factor, t raised to the alpha. You pull out a t from the second one, t raised to the beta. T raised to the alpha times t raised to the beta is t to the alpha plus beta, which is greater than t whenever alpha plus beta is greater than 1. It's less than 1, or decreasing returns to scale, whenever alpha plus beta is less than 1. These should be less than or equal to's, not less than strict things. It's strictly increasing returns to scale if alpha plus beta is strictly greater than 1. And it's constant returns to scale when alpha plus beta is exactly equal to 1. When might we see different kinds of scale returns to scale, right? So increasing returns to scale says that as I add people, sort of the marginal value of those changes, and I'm not changing one. When I say marginal value, I don't mean the marginal value of labor or capital independently. The marginal value of increasing both capital and labor seems to be increasing. And why would that happen? It's something like a network effect, right? In situations where I have groups of people who work collaboratively, there's increasing returns to scale because they can share information, they can work as a team, they can specialize on the parts of the project that they're the best at. And so you'd get increasing returns to scale, at least in certain parts of your production function, because of these kind of network effects. Constant returns to scale is more like that factory example, right? Ford opens a second factory in a different location. It works exactly the same as the first factory, with the same amount of labor, same amount of capital. It does exactly what the other one did, and so you're just going to double your production, right? You double the number of factories you have, you double the production. They're unrelated. They're not interacting with each other in any way. Decreasing returns to scale is generally when you hit some kind of some resource limitation. Often it's a thought of like crowding out, right? So if you have a fixed amount of time or land and you just pile more people into it, they're just going to bump into each other. Or you pile more tractors into it, they're going to bump into each other. So decreasing returns to scale is, I think, the overwhelming thing at the global scale, right? If you just keep increasing the inputs without bound, eventually it sort of feels intuitive that you're going to become decreasing returns to scale. Again, these do not have to be everywhere, right? It could be increasing returns to scale in the beginning and then eventually decreasing returns to scale. And so in the beginning, you might gain some expertise. You might have people specializing. You might have people sharing information, and you double your office size, and you get more than twice the production out of it. But eventually, you're going to have people just kind of sitting idle. They're not doing anything. They're bumping into each other. There's complexities from the size of the workforce. And so you get bloat or something like that. You might hit the fixed, the size of the building. People are sitting on top of each other. And so you eventually have decreasing returns to scale. One thing to note is that a constant returns to scale production function is homogeneous of degree 1 by definition. So the marginal productivity is then homogeneous of degree 0. So that was a math, as if you remember back from math camp or whatever, the first week of this class when I gave you a bunch of math definitions you probably don't remember. If a function is homogeneous of degree k, then its first derivative is homogeneous of degree 1, k minus 1. So that means the marginal productivity here of k and l is equal to, is homogeneous of degree 0, which means if a constant returns to scale function, if a production function is constant returns to scale, then the marginal productivity is constant, which makes sense, right? If doubling your inputs is always doubling your outputs, the relative rate of change is not changing based on how much capital and labor you have. It's just the ratio of capital and labor. So we can look at that in a graph. You have these isoquants which are extending. They're sort of parallel to each other with respect to the rays coming out of the origin. If you just move up along, these different planes, the slope of the budget lines, the slope of the isoquants is not changing. So as you move from one isoquant to another, their slopes stay the same as long as the ratio of capital to labor remains fixed, which means that you're on the same ray or originating from the origin, emanating from the origin. So this is a nice way of looking at like the graphical sort of interpretation of a homogeneous of degree 1 or constant returns to scale production function.